In this video, we're going to look at the difference between ordinary integration and Monte Carlo integration. So in the MATLAB window in front of us, we can see a function which I've defined called integral value equals MC integrate. So this MC integrate function is going to integrate some function that I've defined. And the function I've chosen here is just some particular function, x cos x plus 4 sine x. And I'm going to want to integrate it from 0 to 2 pi. So within this overall function, I've defined a subfunction that defines the value f of x, which is this expression here. And I'm going to take these values of x and I'm going to accumulate the integral at each value of x by calculating y at each value of x and then adding that value of y to the integral. And of course, by beginning at the value 0, I can accumulate the integral and work out what it is. Now, I have to loop over the number of x samples that I have. So this is just an easy way of doing that. I just calculate the set of x values, and when I accumulate the integral, I need to divide by the number of samples I have. That's what gives me the step size automatically. You know, the area of each of those little parallelograms. If we think of this integral as being an integral by adding up the little pieces of area stepwise. So I can do this calculation, I can run it, and what I see displayed is I see all the x values that I've obtained and all the corresponding y values. And the integral in this case, of course I can calculate this one analytically, and if you check that the integral of this function from 0 to 2 pi should be 0, so the total integral I have should be around about 0, which it is. And of course, if I run this successive times, I always get the same answer because, of course, I'm always using the same values of x. And I can reduce the step size. This will take a little bit longer to run. And you can see that the integral gets closer and closer to 0. And on the right here, I can see a large number of points, and just to show those points a little more clearly, I can remove 2 decimal places. I can have a larger step size, and I can see the individual points. And as expected, the accuracy of this integral becomes poorer with a smaller number of points. Now let's look at what I'm actually doing. You can see in this calculation that what I've effectively done is when I calculate the integral, I have effectively averaged the value of f of x over the range from 0 to 2 pi. So I add up all the values yi that I have over here, and I take their average by dividing by the number of samples. So you can see that this integral, if I look on the right hand side, this integral, or the procedure of calculating any integral over some range, is the same thing as calculating the average of the function over that range. Now this suggests another way that I can select the points. Rather than selecting them uniformly over the range, I could replace this calculation, this set of values here. I could, instead of using uniformly spaced variates, I could have randomly selected variates. So how would I do that? Well, I could simply replace the range here by multiplying a random number from 0 to 1, like so, and multiplying that by 2 pi in order to get the range from 0 to 2 pi. And of course I can change that to any range by adding a number at the start to give me a starting point and appropriately scaling this value. And if I want to have, say, 1,000 samples, I simply do 1, 1,000 to generate a 1 by 1,000 array. So I've now replaced that uniformly spaced set of x values with a randomly selected set of x values, but everything else should be the same. All I've done is I have calculated the average of f of x over the range from 0 to 2 pi. So what happens when I do that? Let's run it. And you can see that it looks pretty much the same. The only difference is the points which are displayed on the right hand side are the randomly selected values of x over that range and the corresponding values of f of x. And if I were to run this calculation again, the difference now is that those points are changing each time I do the calculation. If you see on the right-hand side that those points are changing. So the calculation is much the same, except I only get a statistical measure. But how this is beneficial over normal integration is that if I look at the fluctuation of those returned integral values, I get directly a measure of the error inherent in the calculation. And there are some caveats to that, but that's loosely speaking correct. And if I increase the number of samples that I'm using, I can get a slightly better answer. And you can see this calculation can proceed quite quickly. And again, I run it. And as we saw in a previous calculation, a previous video, the accuracy of the integral that I obtain goes as 1 over the square root of the number of samples, more or less. So that's the difference between ordinary integration and Monte Carlo integration when applied to a simple function such as this function I've chosen here.